Welcome to this YouTube presentation regarding dehydration and how we can use biosignals and scientific measurements to help individuals track their dehydration state. I'm Anirudh Ajay, and joining me throughout this presentation is Hussain Motiwala. So our primary motivation in the engineering department largely focuses on athletic performance. Many athletes wish to have peak performance throughout precise and lengthy practice sessions. And with how important hydration is to keeping up this maximum efficiency during those practice sessions, a mere 15 minutes in an exercise state can lead to dehydration. But on the flip side, there's also a situation where only 600 milliliters and 45 minutes can be used to rehydrate the athlete. So it's a very simple issue that can be solved, but in order to detect this problem earlier on, we need a device or a method to quell these dehydration issues before they could occur. So we're going to be taking a look at a graph using pH to perhaps find an avenue to create a device here.
This graph plots sweat pH measured over time during exercise. As Anirudh stated, it can take as little as 15 minutes for someone to go from a fully hydrated state to a state of dehydration. This is why it is essential for people like professional athletes to know their hydration state and when they need to drink more water so that they can maximize their performance. To explain how the sweat pH biosignal originates, first we must establish some background information based on our extensive literature search. Humans go through a hydration-dehydration cycle which is governed by the intake of water, and sweat pH is a good measure of hydration state. There are many factors that determine how long it takes for a person to get dehydrated from a fully dehydrated state. It can take a minimum of 15 minutes to get dehydrated while exercising, roughly 45 minutes to an hour to get rehydrated after drinking water, and although there is limited research on how long it takes for a person to get dehydrated in a state of rest, the longest anyone can survive without water is roughly 8 days. Human sweat leans more on the acidic side and ranges anywhere from a pH of 4 when hydrated and 7 when dehydrated. A typical digital pH probe works by comparing the pH of the sample solution to a neutral buffer solution of pH 7 and sends a voltage signal proportional to the pH of the solution, which can then be processed and examined. The pH measured by the probe ranges from 0 to 14 pH units, which equates to an output of negative 414 to 414 millivolts and an approximate 59 millivolts per pH unit. In this case, our design, we would have a wearable device which has a miniature pH probe that measures the pH of the sweat secreted from the skin and sends a proportional voltage signal off to our circuit within the device for signal processing. Because the oscillation of sweat pH is correlated with a person's hydration level, peak and trough detection can be used to inform the user about their hydration state in real time.
So looking at our circuit design, this is just going to be a quick overview. Essentially, after accepting the voltage from the biosignal, in this case sweat, we amplify the signal via an inverting operational amplifier. In order to actually use this amplified signal, however, we must return it to a usable form, and that's where stage 2 comes into play of the inverting operational amplifier being used again. Finally, stage 3 is a passive bandpass filter that's going to be used to eliminate any noise within that received biosignal that's been amplified and is finally sent to the microprocessor for analog to digital conversion and then the final calculations as to the dehydration state of the athlete or individual for that matter.
The gain we set for our inverting amplification stage was about 12. We set this as the gain because a typical microprocessor operates at a voltage of plus or minus 5 volts, and amplifying a signal with a max amplitude of 414 millivolts by a factor of 12 allows our signal to be amplified to a safe maximum. Our resistor values were chosen based on standard available resistors to fit our design criteria. An inverting operational amplifier setup was chosen for this gain stage of our circuit because the ratio of the resistors is directly correlated with the gain applied by the components. This way, if a new type of pH probe with better accuracy but with a different instrument voltage output range is wanting to be implemented, all that needs to be changed is the probe and the value of the negative feedback reference resistor.
Due to the inverting nature of our amplification stage amplifier setup, following the amplification stage, we have an additional inversion stage which does not apply any amplifying gain, but again inverts the signal back to its original state. This secondary inversion stage is necessary so that the final output signal accurately represents the person's sweat pH and allows for accurate detection of peak or dehydration state and trough or hydrated state.
The last stage of our circuit filters out high frequency noise and unwanted low frequencies by attenuating those frequencies using a passive bandpass filter. The cut on and cut off frequencies were chosen based on maximum and minimum peak to trough periods of 8 days and 15 minutes for dehydration respectively. The allowed frequencies range from 700 nanohertz to 600 microhertz, which encompasses all the important frequencies for dehydration and rehydration time. These minimum and maximum frequencies were used to calculate the RC factor needed for each of the low pass and high pass portions of the bandpass filter. The reason we decided to use a bandpass filter for this application instead of a simple low-pass filter was that with a device so small, we do not want to be wasting power amplifying and passing unusable, extremely low frequencies. This issue was resolved by the high-pass portion of the bandpass filter.
To conclude the bonus video here, we wanted to break down the portions of the assignment that we did separately and then the ones that we collaborated on. Anirudh, Ajay, me, largely went towards the video editing side of things, while Hussain, he helped us with the script creation. And then in the presentation itself and the voiceovers, obviously you saw that this was done more in a collaborative sense, and together this is the presentation that we have finally completed. And to end, here are our works cited that will also be available in our literature project later on. Thank you.